first research paper along these lines that I've seen in a while that has caught my eye. And then so this is called GraphReader, Building Graph-Based Agent to Enhance Long Context Abilities of Large Language Models, which is a very long title. And then it's put out by Chinese research organizations. But I want to point out a few things here. So it's put out by Alibaba Group, the Chinese University of Hong Kong, Shanghai AI Laboratory, and University of Manchester. So whenever you see like Chinese research papers along these lines, it's multiple research institutions, usually a commercial institution, and then in this case also a partnership with a Western institution as well. There's a lot of knock just off the bat, when you hear a research paper out of China, but like the research papers out of China, they're coming out really strong for a reason. And then so just highlighting that and pointing that out. And then so this paper is very specifically related to rag tuning and trying to ground a model in understanding. And then so within that, there's a common problem of the man in the middle type of problem, where it's if you take a long context, let's say 126,000 tokens, and then the 64,000 token, like the one in the middle, the model's just going to ignore it basically, like flat out. And there's like almost nothing that you can do about it. Claude 3.5 clocks the best with that, and then the benchmarks I've seen around that are that Claude 3.5 is getting around like 60% on that. And then if we're looking at the benchmarks here, where we're looking at GPT-4 is what they're benchmarking off the just off the flat out, it's like 15% base, right? And then that's true. It's a bad problem overall. And then what you can see is that this is improving the performance of the models in this instance quite significantly. And then what their approach is it's a simple approach overall. It's a graph-based approach, and then so they take the data and they turn it into graph-based data. And then so what they do is they're essentially tokenizing the data into graph-based data is the best way that I can explain it. So let's take a book as an example. We'll take like Harry Potter. So I take the book Harry Potter and then I want to turn it into a GraphReader is what they call it, right? So I want to turn it into graph-based data. So what I do is I turn that into a graph, and then from there I take and I extract the essential information, and they call it the key elements. And then so it will essentially go through and whatever like the key elements of Harry Potter are. So Harry Potter key elements would be like Hogwarts, Dumbledore, like these types of things, magic. And then they would get distilled, and those would be the different plots in the graph. And then essentially that is what the model would ground its information to. And then it would always ground it to these essential key elements within the graph-based interface and within the graph reading that it's doing, essentially. And then the next step that they utilize within this, it's the unique approach is that they utilize this as a agent-based approach and agent retrieval. So they essentially give it their logic overall. If you read through this paper, it's to imbue logical step-by-step reasoning, utilizing this graph-based methodology, right? And then so it's take this big concept, chunk it, take the big concepts of it, graph those big concepts, take the most important concepts of those big concepts, distill those out, graph those out, and then do agent-based actions off of that, retrieval actions off of that, right? And then the kind of the thought is, and the reasoning is that will improve logical reasoning and performance across the board, which they are showing in this paper that is exactly what is occurring. And then so you can see here, they give a very good visual representation of exactly what we're looking at here. And then so they utilize this band. I don't know this band personally, honestly. And then so this person, and then they essentially create concepts around the band, and then so you can see that the key concepts are that this band is from Toronto. They have an album. They're from Canada. They're a gothic band. Danko Jones. I'm assuming that's like the lead singer person, or that's the band name. But so the model is grounding on these key elements, right? And then so it grounds on these, and then it extracts, and then it when it's utilizing its reasoning functioning, it bouncing back and forth after it is referencing from this graph-based interface. It goes through and then retrieves and then bounces out and then gives an answer. And then gives an answer in the reasoning. And then I'll state it as well. So I've trained a model on these same types of things. It's my model that I've trained on. I've rag tuned, so it's like the same type of. They're using ChatGPT 4, right? So I'm assuming it's a very similar setup to theirs. I have a model that's trained on graph neural network data and then PFAF data, which is kind of the same thing. So mine is graph. It's splitting it into graphs and then splitting it into fractals as well. And then that model, like I use that model for everything because it has smoked a lot of models, right? And I've used that model for a while, and then so it's interesting seeing this research paper and then seeing that this is the methodology that they're kind of going forward and going forth within this, because that's essentially like what the goal that I created with that model before, and then you can just see that it's kind of like outdoing a lot of other models within this, right? And then to me, it's the reason why I created it, and I can tell you that up front, is like intuitively, I just like tokenization as it currently exists and word vectorization as it currently exists is not the best path forward with these models. To me, it's the weakest point period with these models, which is why I focused on it first, right? I reverse engineered essentially LLM models like from the ground up. How do you build them? How do they work? How are they constructed? Okay, now that I've done that, what's the weakest point? The weakest point is word vectorization. Why is it the weakest point? Because it sacrifices so much accuracy. It's about 15% or so accurate, right? So you got like 85% play within that. And then so it's like things like PFAF, for example, right? Like PFAF sacrifices accuracy as well. It operates off of the same types of mechanisms that word vectorization does, but like it sacrifices about 15% accuracy as opposed to 85% accuracy, right? And then that was my logic going in. It's just very simple. Like it's not hard to beat something that is sacrificing so much accuracy up front. It's just that people don't understand. They don't want to get into the math of it enough to understand that concept. But it's simple once you dive into these things. And then once you dive into these things, graph-based neural networks is the future. And then it's being shown that it's even effective in rag tuning. And then that's kind of the bottom line. And the last thing that I'll leave within this particular lecture is the fact that if this is working so well within rag tuning, that to me that this shows the pure potential of this, because you're not actually updating the weights to like think fractally overall, or to think in this instance graphically overall, right? Like a graph-based overall. And then so, which is very important because of the fact that taking this a step further is going to improve the performance even more. So if they're getting this performance off of rag tuning, if they fine tune, the performance would jump even further if they do these tests theoretically, right? But so overall, I'll do this lecture here, and then so this is on GraphReader, and then I'll leave a link to the paper. Please check out the paper, and thank you very much for this lecture.